Welcome to this video where you learn how to give great answers to technical iOS interview questions. The content you're about to see used to be a paid training course, but thanks to the generous sponsorship of RevenueCat, it is now available for free on YouTube. So I have a big thank you for them, and if you're curious to see how they can help you integrate in-app purchases into your iOS app, you have a link to learn more in the description. That's all I wanted to say. Enjoy the video. Hey, welcome to this training course to learn how to answer iOS interview questions like a pro. So what's the plan for this course? It's pretty straightforward. First, I'm going to show you a simple framework that you can apply to answer interview questions in a way that feels structured, clear, and impactful. And then I will show you through 10 different examples how to apply this framework to answer typical questions that you could expect in an iOS technical interview. And my goal is that by the end of this course, you will be able to efficiently apply this framework the next time you're taking an iOS interview. Answering an interview question can definitely be stressful. Someone is trying to evaluate you, you're trying to get a job, so the stakes are definitely high, and in that situation, it's very easy to stumble, be a bit confused, and basically deliver your answer in a way that feels subpar. To try and avoid this, I want to show you a very simple framework in 3 steps that will help you deliver your answer in a way that feels clear, structured, and impactful. So let's see what are these 3 steps. The first step is to start by contextualizing your answer. What do I mean by contextualize? I mean that you should reformulate the question and explicitly state any assumptions you're making. You can see this as an introduction for your answer. It's a way to nicely ease into the actual answer and also give a bit of time to the interviewer to fully switch into listening mode. But this is also a great way for the interviewer to correct you if for some reason you've made a wrong assumption. This way you don't waste time starting to deliver an answer that's going into the wrong direction. So once you're done contextualizing, it's time to move on to the next step, which is to deliver the actual answer. Here it's relatively straightforward. You just answer the question, meaning that you give either the explanation, the definition, the best practice that the interviewer is expecting to hear. But after you're done answering the question, it's not over. There is still one last step, which is to recap your answer. The goal here is to sum up the key points of your answer. This shouldn't take too long, just a few sentences, but doing so will really help make your answer feel more structured. And if you have more knowledge on the topic or on adjacent or related topics, this is also a great time to mention it. Don't forget that the goal of the interviewer is to evaluate your skill level in general, and the questions are just a proxy to achieve that goal. And so any extra information you can share that will help convey this feeling that you do know your stuff will only have a positive impact. So these are the 3 steps of this simple framework: contextualize, answer, and finally, recap. Now it's time to see this framework in action to see how we can apply this framework to an actual iOS interview question. So let's apply our framework to answer a first interview question, and that question is: what's an optional? Back when I was interviewing candidates for junior to mid-level positions, I would actually always start the interview by asking this question because I feel it's a nice, simple question and it's a great way to get the interview started. So let's use our framework to answer this question. The first step is to contextualize the question. Here, a great way to contextualize is to remind the interviewer that one of the goals of Swift is to be a safe programming language. This means that, unlike in other languages, variable by default cannot store a null value. This means that if you have a variable that, for instance, is typed with int, then the compiler will expect that variable to hold an actual int, and it won't be possible to set a null value to the variable. But of course, there are situations where it makes sense for a variable to actually hold a null value, and so Swift does offer a mechanism to make a variable nullable, and we opt in to this mechanism by making the type of the variable be an optional. That's more than enough for the contextualization. Now let's move on to the actual answer. We can start by stating that to make a variable be an optional, we add a question mark to the type of the variable, which is nothing more than a shortcut for using the generic type optional of t. And by making a variable optional, the compiler will actually make sure that we explicitly deal with the potential nil value. This is the big advantage of optional. It offers a type-safe approach to dealing with values that can potentially be nil. And we have basically two ways to deal with the potential nil value. First, we can use the safe approach, which is by using syntaxes like optional chaining to call a method on an optional, or conditional binding, the famous if-let syntax. And these approaches allow us to deal with the optional in a way that is safe, meaning that if the value is actually nil, our code won't crash, but we will need to write a bit more code to deal with the potential nil case. And then we have unsafe approaches, like for instance force unwrapping. These approaches will require a bit less syntax because we don't need to deal with the potential nil value, but they have one big drawback, which is that if the value turns out to be nil, then your code will crash. So of course, most of the time, we do want to use the safe way of handling an optional because we don't want our code to crash when there is actually a nil value. And unsafe approaches should really be used with a lot of caution and should be reserved to the rare cases where we are extremely sure that the value will never be nil, and we should never lose sight of the fact that if for some reason, for some unforeseen reason, the value turns out to be nil, then our program will crash. So that's what a potential answer to this question looks like. Now let's move on to the last part of our framework, the recap. Here the recap is pretty straightforward. We can just state that optional is Swift's type-safe mechanism to deal with potentially nil values. And don't forget that the recap is also a great time to share any extra knowledge that you have on the topic. For instance, here you can share the fact that optional is actually implemented in Swift itself. It's part of the standard library, and you can go see its code on GitHub. And optional is actually implemented using an enum with two cases, none and then some with an associated value to store the actual value. However, while this means that we could basically implement our own version of optional, we couldn't implement everything because most of the sugar syntax that makes optional quite easy to use in Swift is itself implemented in the compiler. So that's all for this first question. Now let's move on to the second one. So for this second question, I picked a topic that is slightly more complex, and it's the difference between at-escaping and non-at-escaping closures. So let's see how we can apply our framework to this new question. First, we start by once again contextualizing the question. Here, a great way to contextualize is to give a simple definition of what a closure is. So something along these lines, a closure is a piece of code that we write in one place, but that is meant to be executed at a later time. And then we move on to the fact that because they will be executed later, closures need to make sure that the values they interact with will still be in memory by the time they are executed. And as we know, this ability of closures to capture strong references is a double-edged sword because it also opens up the way to memory leaks through retain cycles. I think that's good enough for the contextualization. Now we can move on to delivering the actual answer. So first, we can start by stating that not all closures are meant to be used the same way. We can really split closures into two different kinds. First, we have the closures that are not meant to have a lifetime that exceeds the one of the function that they are passed to. A typical example of such closures are the ones you pass to functions like map or filter. These closures are meant to be called inside the body of the function that you pass them to, but once that function has returned, they no longer serve any purpose. And these are the closures that we call non-escaping closures. The name reflects the fact that these closures don't escape the scope of the function they've been passed to. And because their lifetime is limited to that of the function they've been passed to, they don't pose a threat regarding memory safety because they cannot create a memory leak since their lifetime is limited. This means that inside a non-escaping closure, we don't actually need to worry about capturing a strong reference because it's just not possible for such a closure to lead to a retain cycle. And in Swift, closures are actually non-escaping by default. However, some closures do have the legitimate need to outlive the function that they've been passed to. Think for instance of the closure that handles the result of a network call. Such a closure will be executed after that the function that started the network call has returned. Such closures are called escaping closures because they escape the lifetime of the function they've been passed to, and in Swift, they must be explicitly annotated with the attribute @escaping. And inside such closures, we must be very careful whenever we capture a strong reference to an instance because these are the kind of closures that have the potential for creating a retain cycle. However, Swift does provide us with the tools to capture references in safe manners inside such closures by using the closures capture list. A typical example of this is when we capture a weak reference to self inside a closure that will be directly or indirectly also be stored in self. I think it's more than enough for the answer. Now we can move on to the recap. So for the recap, we can just state that closures are known to be one of the top causes of memory leaks in iOS, but not all closures have the potential to create such memory leaks. Only closures that escape the lifetime of the function they're passed to can potentially be harmful. And that's why Swift forces us to explicitly annotate such closures with @escaping. But you want to be careful because there does exist some rare instances where @escaping will actually be implicit. An example of that is when you pass an optional closure as an argument. In that situation, the @escaping attribute won't be explicitly written, but the closure will still behave like an escaping closure. That's all for this second question. Let's move to the next one. So with this new question, we're going into the topic of good practices and code readability. The question is, when would you use a computed property versus a method? Once again, let's apply our framework to answer this question. We begin by contextualizing our answer. So here, a great way to contextualize the answer is to just reformulate the question. So we can state that in Swift, when we want to encapsulate a piece of code that produces a value, we basically have two potential choices. We can put that piece of code either inside a computed property or inside a method. And the interesting thing here is that from a technical point of view, computed properties and methods are actually quite similar. When you think about it, a compute property is actually nothing else than a method with no argument and a simplified syntax to call it. And because of that, the choice between the two options cannot really be decided from the technical point of view, but rather should be decided from a semantics point of view, meaning we should consider what the code actually does. Because in Swift, properties are expected to have some specific semantics. They shouldn't have side effects, meaning that calling a computed property should not produce a side effect in another part of our code. They should also be idempotent, which is a mathematical word to say that if we call the properties several times successively in a row, it should always return the same value. So for instance, a property shouldn't be used to implement a random value because getting a random value is definitely not idempotent. The entire idea is to get a different value every time. And finally, properties should execute in constant time. So in terms of time complexity, they should be big O of 1, meaning that if, for instance, you call a compute property on a collection, the time the property will take to execute should not depend on the size of the collection. If all these properties are met, then it's absolutely okay to encapsulate our code to produce a value using a computed property. However, if not all of them are met, then it's better to use a method because the code we have doesn't behave like we expect a property to behave. Because if we were to still encapsulate the code inside a compute property, it's basically guaranteed to generate trouble at some point when another person will use the property and will expect it to behave in a way that it doesn't. So that was a big answer. Now let's move on to the recap. So for this recap, we can conclude by stating that syntax sugar, like compute properties, can be really useful to write shorter code. However, we must be really careful to only use syntax sugar when it actually makes sense. And it's usually a bad idea to try to use a syntax sugar when not 100% of its requirements have been met, because it's basically guaranteed to lead to trouble at some point. So for this fourth question, I chose something that is still on the topic of code readability by asking what is the purpose of the Swift keyword guard. Once again, let's apply our framework to answer this question. So how can you contextualize this question? You can start by saying that when we implement a feature in an iOS app, we usually split our code into two parts. First, we have what we call the happy path, meaning the code that implements our feature assuming that everything is working correctly. And then we also have the error paths, which deal with all the potential technical and business errors that can happen. So think of things like having no network connection, having an expired authentication token, using an invalid promo code, that kind of things. And ideally, we would like the structure of our code to be such that the happy path is the main flow of the code and the error paths are branching out of this main flow. However, if we implement our code using if statements to make sure that all the conditions are met, it's actually the opposite that will be happening. What will happen is that each new error path, and so each new if statement, will cause the happy path to become more and more deeply nested. And as we can imagine, this is when the keyword guard comes into play. Guard will allow us to reverse the structure of the code by implementing an early return from the function whenever a condition has not been met. And so by using guard, we will be able to refactor our code into a much more readable structure with the happy path at the center, like we initially wanted. So that was the answer. Now let's finish with the recap. And for the recap, we can simply state that guard is the typical example of when seemingly simple sugar syntax actually has the potential of dramatically improving the readability of our code. However, like with all sugar syntax, we want to be careful because they always come with a flip side. In the case of guard, we want to be careful when using a negation inside the condition, because then the statement ends up being a double negation, which can be hard to read and potentially confusing. For this next question, I picked a much more open topic by asking to give an example of a bad practice in Swift. So once again, let's answer the question using our framework and start by contextualizing the question. Here we can contextualize by stating that a bad practice is usually a situation where what initially felt like a good idea actually turned out to have harmful consequences. And a typical example of such a situation in Swift would be when you try to use an advanced language feature in a context where it wasn't really meant to be used, and it ends up doing more harm than good. Let's take the example of the keyword defer. Defer is a keyword that allows us to write code that will be executed only when the current scope exits. So typically when a function returns. Defer can actually be very useful when we are dealing with symmetrical operations. So think of things like opening and closing a file, starting and stopping a process, allocating and deallocating memory, that kind of thing. Because forgetting to make the symmetrical call would be a dangerous programming error, defer is actually very useful in this specific situation. However, it is very important to realize that defer works by breaking a very important property. Indeed, defer decouples the place where the code is written with the time when it is actually executed. This means that when we use defer, we can no longer assume that our code will be executed in the order in which it was written. When we are dealing with symmetrical calls, the upside of using defer make this change definitely worth it. However, in other contexts, using defer could very easily turn out to be a bad practice because it is almost guaranteed to make our code more confusing without necessarily providing a significant improvement in exchange. That's all for the answer. Now let's move on to the recap. And for the recap, we can say that Swift is a very rich programming language with a lot of advanced features, but we must be careful when using them because their indiscriminate use can very quickly turn into bad practices. And this isn't even specific to Swift because software engineering as a whole is a lot about making the correct trade-offs. And so, as a general rule, whenever we want to use a fancy trick, we should always be thorough and carefully consider both the potential upside but also the potential downsides. So for this sixth question, we are back to a very technical topic because the question is, what's the difference between weak and unowned? And because it's a very technical question, it's actually quite challenging to deliver an answer that will both be correct, but that will also feel very structured and very clear. So let's see how our framework can help us here. With this kind of very technical question, the best way to contextualize is to just give very clear definition of what we are talking about. So here we can state that weak and unowned are two attributes that we can use to refer to an instance without taking a strong reference to it. And we typically use weak or unowned in situations where taking a strong reference to an instance would result in a retain cycle, for instance, inside a closure or when storing a delegate. That should be enough context. Now let's move on to the answer itself. To answer the question, we begin by giving precise definitions of weak and unowned. A weak reference is meant to be used when the other instance has a shorter lifetime. Because of this shorter lifetime, it's possible for the other instance to be deallocated by the time that we use the weak reference. To account for this possibility, the weak reference will be stored using an optional. This way, when the other instance has been deallocated, the weak reference will store nil. And on the other hand, an unowned reference is meant to be used when the other instance has an equal or longer lifetime. And because of this equal or longer lifetime, we assume that the other instance will never be deallocated when we use the unowned reference. Consequently, an unowned reference will be implicitly unwrapped. That's more than enough for the answer. Now let's tie everything together during the recap. We begin the recap by stating that both weak and unowned references allow us to refer to other instances without the risk of creating a retain cycle. However, we definitely want to be careful when using unowned references, because if our assumption that the other instance will have an equal or longer lifetime turns out to be wrong, then accessing the unowned reference will result in a crash. So if we want to play it safe, it actually makes sense to only use weak references inside a codebase. It's worth noting that because a weak reference has to deal with the extra logic for the case where the other instance has been deallocated, it is a little less optimized than an unowned reference. However, unless you're writing some computation-intensive code that requires every possible optimization, there's a very good chance that you will never notice any difference in performance by using a weak reference over an unowned reference. The seventh question is, when would you use the attribute at autoclosure? That's an interesting one because with such a question, the interviewer usually wants to evaluate two things. First, they want to see whether or not you know what the attribute at autoclosure is, and then they want to see if you have enough coding maturity to know when it's a good idea and when it's not a good idea to use such an attribute. So let's answer the question. By now, you should have a good idea of how to contextualize that kind of question. We contextualize it by giving a definition of the attribute in question. So here, at autoclosure is an attribute that we can apply to a closure argument of a function. And when that attribute is applied, then the expression that we pass as an argument will be automatically wrapped inside a closure. This behavior might seem weird at first glance, but it actually serves an interesting purpose. Imagine that the expression you pass as an argument is potentially expensive to compute, and that at the same time, the function you pass it to might not always need to use it. In that situation, it would make a lot of sense to have a mechanism that would allow the costly expression to be evaluated only when we need to use it. Wrapping the expression inside a closure would achieve that goal, but it would also degrade the readability of the call sites because we would need to add a pair of curly braces every time. And that's when the attribute @AutoClosure becomes useful. This attribute will automatically wrap the expression inside a closure. This way, we get all the benefits without degrading the readability of the call sites. A typical example of when @AutoClosure can be useful is if we want to implement a logging function, because logs are not always enabled, or all not logging levels are not always enabled, and the data we log can be costly to evaluate. Think, for instance, if we are dumping a big object hierarchy. And now that we have explained when it would make sense to use @AutoClosure, let's tie everything together by moving into the recap. We can start by saying that while @AutoClosure can definitely help us optimize our code without degrading its readability, like with any sugar syntax, it's important to also consider its flip side. In the case of AutoClosure, it's not obvious at the call side that the expression will be wrapped inside a closure, and so will not be evaluated immediately, if at all. And it's important to keep this in mind because it could lead to subtle bugs in potential edge cases, like, for instance, if we pass as an argument an expression that also carries out a side effect. For this 8th question, we are back to a much more open topic with the question, what open source tools do you recommend using and why? With this kind of question, the contextualization is usually quite easy. We can just say that the iOS community has a very active open source scene, which produces a lot of useful tools to improve the quality of a project. And while it's near impossible to go over all the possible valuable tools, we can definitely go over the most common ones. We can begin by talking about SwiftLint and Swift Format, which are two linters that make it easier to enforce coding rules and coding style across our codebase. Then we can talk about Fastlane, which is an extremely popular command line tool whose goal is to automate the shipping process of an iOS app from signing the code to uploading it to the App Store. Then we can talk of SwiftGen, which is a great tool that will generate Swift data structures so that we can manipulate the resources of our Xcode project in a type-safe manner. And while we're on the topic of code generation tool, we can also mention Sourcery, which is a general purpose code generation tool that can be very useful to automate the writing of boilerplate code. Think, for instance, of implementing mocked implementation of protocols. And finally, we can mention that older projects are very likely to use an open source tool to manage their dependencies with tools like CocoaPods or Carthage. However, more recent projects are much more likely to use Apple's own Swift Package Manager for this job. And for the recap, we can say that there are a lot of useful open source tools out there that do a great job at providing the features that are still missing from Xcode. But of course, the goal here is definitely not to bloat our project by using every open source tool possible, but rather to carefully evaluate whether a tool is actually relevant to our current needs or not. We are getting close to the end. This is already question 9, and this is a very interesting question. How do you choose the minimum version for an iOS app? So let's answer it and start with a bit of context. Here it can be useful to remind that all iOS apps must decide what is the lowest version of iOS that they support. And because new APIs are, unless exception, not backported to older versions of iOS, this choice has some strong technical consequences. For instance, SwiftUI isn't available before iOS 13 and, to be honest, only becomes really usable with iOS 14. The same way, Combine also isn't available before iOS 13. And so, because you might not be able to use important APIs, the choice of the lowest iOS version your app supports will have some major consequences on the technical choices you will be making as a developer. However, this very important choice cannot be only decided from the technical point of view, because as developers, we would of course like to support only the most recent version. This way, we would get access to all the modern APIs, and we would also save a ton of time testing our app on older versions of iOS. But doing so would also make our app unusable by a potentially large amount of iPhone users. And this is why this choice not only has some strong technical implications, but also strong business implications. And there's no clear-cut answer here. It really depends on the kind of app that you are working on. For example, apps that deliver important services like banking or the administration will usually want to support a large number of iOS versions. And on the other hand, apps that deliver cutting-edge tech can assume that their users update their device more regularly and so can afford to support less iOS versions. That was definitely a long answer, so now it's time to move on to the recap. We can recap by stating that deciding the minimum version of iOS that an app will support is definitely not an easy choice and is often the result of a compromise between business and engineering. And one important thing to keep in mind if you're about to start a new app is to make sure that you decide its minimum iOS version based on when the app is actually expected to release, which could very easily be months or even a year away from now. So we've reached the last question of this training course. This one is all about architecture and design patterns, and the question is, can you explain what's dependency injection? As usual, let's answer the question using our framework. So we start by contextualizing the question, and we can contextualize by saying that it's a good software practice to partition our code in several components, each tasked with fulfilling a specific responsibility. But of course, the question that comes immediately after saying that is, how do we put all the pieces of the puzzle back together? A naive but working approach would be to make each component responsible for both creating and using its dependencies. And while this would work, it would also strongly decrease the modularity of our codebase because it would then become impossible to swap one component for another. And to solve this issue, we need a way to decouple the creation of a dependency with its actual use. This process is exactly what's called dependency injection, and here's how it typically looks like. First, we make each dependency expose its API through a protocol, and then we update the initializer of our component, adding a new argument for each dependency and using the protocols as the types. This way, the actual creation of the dependencies can be handled in a separate part of our code, and our component can focus solely on using its dependencies. As a result, our codebase has become much more modular. We can, for instance, inject mocked version of our dependencies when we run our tests. For the recap, we can start by saying that dependency injection is a typical example of using a $5 word to describe a 50-cent concept because the name sounds super complex and intimidating, whereas the actual idea behind it is relatively simple and straightforward. It's also worth saying that this way of implementing dependency injection is not always possible because it requires you to have control over the initializer of your component. And we actually have a great example of this on iOS. You might have noticed that views defined in a storyboard don't have their subviews injected through their initializer, but rather through properties that are implicitly unwrapped, the properties annotated with @IBOutlet. And the reason for this choice is because back in Objective-C, it wasn't really possible to create a dedicated initializer for each possible combination of dependencies. So that's it, you've reached the end of this training course. I hope you've enjoyed it, that you've learned new things, and that you now feel more confident to answer interview questions. If you want to apply what you've learned, I've put together this list of 10 new questions that you can try to answer using the framework we've just learned together. Once again, thank you for watching this training course and see you next time.